Hi, everyone. Welcome to this meeting. We're in week 7. Today, we're going to be talking about clustering. And so I think it is about time. So I'm just going to go ahead and jump right in. So first, starting off, what is clustering? Clustering is a method of grouping data points based on similar properties. So if you look over here, you have these kind of clusters of data. You have this one over here, this one over here, this one over here. And the idea of clustering is grouping them based on the ones that are close. It is generally an unsupervised learning model method, which means it doesn't require the input data to be labeled. This means you can do it with unlabeled input data, which is very different than everything we've been covering so far, generally. Yeah. So let's look at why we would use clustering, what we would use it for, et cetera, et cetera. The general thing that it's used for is to sort data into distinct groups. And why would we want to do that? Well, some of the use cases for this specific step are recommendation algorithms, and we'll get to that in a second. But another kind of byproduct that it has is it is good at anomaly detection, which means if we go back a couple of slides to this picture, let's say there was a point over here. Some of these algorithms would not categorize that into any of the clusters because let's say you have this cluster, and this cluster, right? You had one over here. It wouldn't make sense to put it into any of those. And that would be considered an anomaly. And anomalies are generally good for kind of recognizing if a data point needs to be dealt with specifically, or maybe in medical cases, if there's an anomaly, you know that, oh, there might be something wrong with the person, or they might have some kind of diagnosis, et cetera, et cetera. Back to anomaly detection. It checks out the points not in the groups. So over here, it might find a group here, it might find a group here, and then these would be the anomalies. And so this is kind of a sign of something possibly problematic going on. And as I said earlier, that is kind of good for medical applications. Recommendation algorithms, as I said earlier, the whole point of clustering is to put data into distinct groups. And when we do this, it's good for something like, if we think about Netflix's recommendation algorithms, it has all of these different movies, TV shows, and they are kind of labeled as maybe more serious, more casual, faster paced, slower paced, et cetera, et cetera. And what a clustering algorithm would do is it would put them into clusters. It would say, okay, these are all pretty close together. You can think of it spatially, but in reality, it's looking at the attributes as in speed and seriousness, and it's using that as kind of the spatial map to look at it and see which things are close. So things that are close will be things that have similar speed and similar seriousness. So something like over here, we have a group of things that are just generally very fast. So Red Notice, Adam Project, Arcane, those are very, very fast-paced shows and TV shows that Netflix has. And maybe it would put them in a cluster using the clustering algorithms. And then the recommendation would then, if you watched something, say like the Adam Project, it would then recommend Arcane and Red Notice because those are all in the same cluster. Similar for Black Mirror. If you watch Black Mirror, it will say, hey, Breaking Bad and Squid Game are both in the same cluster. We'll recommend these movies or TV shows to someone who's already watched Black Mirror. So that's kind of the application of clustering. That is one of the big, like, why you would use it. Moving on to how does clustering actually work? So again, for us, we take a look at this. Even without the green and gray outlines, we can pretty easily tell these dots are kind of all close together. These dots are kind of all close together. Maybe we would include this one right here. Maybe we wouldn't. And then these are kind of not spread out. So visually, as human beings, we can see clusters. We can see them and we can point them out and we can identify them. But computers can't do that. So instead, they have algorithms to do this for us. And that is what we're going to be covering today. So again, the algorithms are clustering as a whole is taking these algorithms and applying them to data. So there are 4 algorithms that we're going to be covering today. And if you noticed earlier when I said that clustering was unsupervised, I had an asterisk. And this is why. Unfortunately, k-nearest neighbors clustering is not unsupervised. You do need to start with labeled training data. But for all the others, you can use unlabeled data and it will find clusters within them. Just a quick overview, k-nearest neighbor functions by generally taking a point and looking at the nearest points to it and seeing what clusters those points are in and assigning it based on those. K-means clustering, again, I'll go over all these in detail throughout, but just to give you kind of an overview. K-means clustering takes a couple of means. It takes a couple of averages. You can think of them as kind of centers of the clusters, and it shifts them around based on where the points that fall into those clusters are. And eventually it'll shift to accurately describing the clusters. Mean shift clustering is similar. You can think of it also as taking a point that's the center of a cluster and moving that point around towards where most of the points that fall into that cluster are. And I'll get into all of this. NDB-SCAN clustering, it's a little more complicated, and we'll touch on that a little bit, but it's just very cool, so I really wanted to include that in this presentation. Before I move on, any questions about what I've just covered, that being what is clustering and the applications of it? No. Okay, cool. So starting with the very first algorithm, k-nearest neighbor clustering. So again, as I said before, this does require training data. And the main idea is to check the k-nearest neighbors and determine which cluster we're going to put the data point we're looking at based on those. So it looks at each individual data point one at a time and sorts it into a cluster. So let's go to the steps. So first, you're going to take your training data that you already have, the labeled training data. This will be a bunch of data points, and each of those data points will already be sorted into clusters, and each data point will know what cluster it is within. Then you're going to place your unlabeled test data in the space, and I'm going to kind of go through with this diagram how it works. So let's say these, ignore the numbers for now, but these colored dots, the blue, red, and green ones are all part of your training data that are already sorted into clusters. We have a blue cluster, a red cluster, and a green cluster. And so these two are in the blue cluster. This one, and this one are in the red cluster, and then the green one is in the green cluster. So if we take this white dot is our unsorted data point that we're trying to figure out what cluster it's in. Using k-nearest neighbors, we would come up with some kind of K. You could do this empirically, you could do this by testing, you could do some kind of prior training with this, but we're just going to pick an arbitrary number of 3. So with the arbitrary number of 3, we're going to look at its 3 nearest neighbors. So this white dot, we're going to look at the 3 closest dots to it. That would be this one. This is the closest. This one is the second closest, and this one is the third closest. Now, if you look, we have a blue, and a red. Those are its 3 nearest neighbors. Does everyone agree? Awesome. So we have 2 blues and a red. And what we're going to do is figure out what the most common cluster is. So 2 blues and 1 red, the most common is blue. So given k equals 3, k nearest neighbors would sort this white dot into the blue cluster. Now let's take a look at something a little bit. Let's say we had a higher k value. Let's say k equals 6. We would take a look at its 6 closest neighbors. Fortunately, there are only 6 dots here, so that's pretty easy. We have 1, 2, 3, 4, 5, and 6. We take a look at all of these because we're doing this with k equals 6. And we see 2 blues, 3 reds, and 1 green. Now, in this case, the most frequent neighbor would be reds because there's 3 of them and only 2 blues and only 2 greens. So if we use k equals 6 for k nearest neighbors, it would sort this white dot into the red cluster. Any questions? No? Okay, awesome. Again, this is just kind of a table kind of describing what I just described, as in first putting the data on the same place as pre-trained data, calculating the distances, finding the nearest neighbors, because in reality, when you're doing this with a computer program, you need to look at all of the data points because you don't know which ones are closest by eyeballing it. So what you're going to do is you're going to measure the distance from the point you're trying to assign to all of the other points, figure out which ones are the closest, take the k closest. So I think here it's taking the 4 closest, so k equals 4, checking what's most frequent. In this case, it would be yellow. And so in this case, as they say here, the white point would be assigned the cluster of yellow. Okay. So just to kind of talk about, I say distance a lot. there's many different ways you can define distance in coding. Generally, we think of distance as the literal length from point A to point B. This is a general way of doing it. This is how most people do it. This is how most code does it. It's called Euclidean distance. However, there's a couple other ways to do it. You can do Manhattan distance, which is if you think about not doing diagonals. So the distance in the X and the distance in the Y. And then if you're in 3 dimensions, you do also plus the distance in the D or Z, just all added up. And different distance algorithms can make different algorithms work slightly differently, but generally we're going to use Euclidean distance. And then there's also Hamming distance, which is very specific in its applications. So before we move on to k-means, any questions about k-nearest neighbors clustering algorithm? Okay, cool. K-means algorithm. So this is a slightly different sort of clustering where instead of looking at the individual data points, we're going to look at the clusters themselves. So we're going to start with k number of centroids. And when I say centroids in general, when we're talking about clusters, a centroid is the center of the cluster, so the middle of it. So we're going to start with k of them. In this case, we visually see that there are 3 kind of groups. And so we're going to start with k centroids. At other times, you can do different ways of figuring out what k is. But in the previous case, k nearest neighbors, k was how many neighbors we're looking at. In this case, it's how many means we're starting with. So how many centroids, how many clusters we're going to have. So in the end, we will have k clusters. So if you end up having, let's say, 3 clusters visually and you choose k equals 4, it means one of those clusters will be split into 2. So how this works is you start with the k centroids and you match and classify each data point to the nearest one. So let's say the x's are centroids over here. We are going to look at each point and give each point or assign each point to the cluster of the nearest centroid. So this x is green. That means all dots who are closest to this x than any other x are going to be green. This x is purple. So all dots that are closer to this x than any other x are going to be purple. This x is red. So all dots that are closest to this x than any other x are going to be red. Then what you're going to do is take the mean of all of the data points that are assigned to that centroid. So essentially what this means is you're going to take the average location of all the points that are assigned to it. So over here, let's just specifically look at red for now. Each of these data points has a location, and you're going to look at only the ones that are assigned to red, and you're going to take the average location out of all of them. That just means adding up all the x and y's and then dividing by how many there are. And then we will get the center of that cluster. Then what we're going to do is we're going to move the centroid that determines what clusters the data points are in to that new center. So again, move the centroid to the new calculated center. Then we're going to have new centroid locations, and we do this process all the way from classifying each data point all the way over again. So after you move the centroid, you classify each data point to whatever cluster it's, to whatever centroid it's nearest, and then you shift the centroids based on the average of the data points within it. This will be a little, this will make a little more sense as we go into the next couple of slides. So step 0, we have all our data points. Step 1, we are going to place our centroids, and this is done essentially randomly at the very beginning. So you see one is right here, one is right here, and one of them is right here. Then what we're going to do is we're going to add up the averages of the points that make it up. So if you see over here, let's look at green. There's a lot of points right here and a lot of points right here. So the average for green is probably going to be somewhere right here if you average the locations of all the points. And if we look at the next slide, we then move it to the new average. And same with all of these moved up a little bit. And if you see, this point is now closer to this centroid than this centroid. So then what's going to happen, we're going to repeat this process. This centroid's now no longer being calculated with the green. And so the green is going to shift a little bit further this way because it has less points over here. And then this purple is going to shift up probably a fair bit because of all the ones up here that are assigned to it. So let's take a look, see if that actually happens. Yes, purple shifted up, green shifts a little bit, red shifts up. We continue repeating these steps. And you can see these clusters start shifting towards forming the actual clusters. So if we take a look at this GIF, even though we set these centroids to places that didn't make sense, that didn't actually work, they eventually shift and sort themselves and show where the clusters are. This is the algorithm working visually. I just said a lot of stuff. Are there any questions on that? Yes. Generally trial and error. And also you can just take a look at the data beforehand and visually see, oh, there's a couple of clusters. I'm going to toss in this many centroids.
There are also mathematical ways to do it. If you guys want to look this up, this is out of the scope of what we're covering today, but I think it's called K-elbow test. I think there's a Wikipedia page for it. Basically what it means is you just plot like, I think the amount of expected variance based off of how many centroids you have. It goes from like 1 up to the amount of data points that are available. Because at that point you can't have any more because every single data point has its own center. And what you do basically is just try and optimize that curve. So you just pick the value where there's the biggest change in explained variance compared to the next step, roughly. I don't know if that's exactly clear, but basically there are mathematical ways to find the exact amount of centers that you need, or the ones that'll do the most effective job.
Thank you. Very good question. Anything else on k-means clustering? Okay. Moving on to mean shift clustering. So when I talk about this, I'm going to talk about, I'll just cover, we're going to think about it as one specific cluster for now. So ignore the fact that this doesn't really make sense practically, but I'm going to explain k-means clustering as how any given cluster is formed. So this is a sliding window algorithm. And the radius of this window is predetermined. So all of these clustering algorithms, you need to predetermine something. For k-nearest neighbors, it's how many neighbors we're looking at. For k-means clustering, it's how many centroids we think there will be. And for mean shift, it's how big of a window we're looking at. So how this works is essentially we have, again, we're going to put the centroid or center of a cluster somewhere. And then what we will do is we will look at all of the dots that fall within its window. And we're going to take this window and calculate, again, as we did with k-means, the average of all the points that fall within the window. We're then going to take that location and we're going to move the centroid there. So very similar to k-means clustering, except we're only looking at the data points that fall within the window. So then we will, again, same with k-means clustering, repeat these steps until the centroid stops moving. I didn't mention it on k-means, but whenever you're repeating this for clustering, whenever you repeat steps over and over again, moving centroids, you generally do it until the centroids stop moving. So if you wanted to write that algorithmically, you could check how much they moved, and when the movement drops to a low enough value, you stop and you say, this is where the clusters are. But yeah, so how this works, again, put your centroid somewhere, check the data points around it, take the average of those locations and move the centroid, and continue repeating that. So this is you see this centroid up here. We look at all of the points around it. You see there's a lot of points down here, not many up here, which means the average of the points is probably going to be around here somewhere. And then it moves, and then we repeat that. We look at all the points within the radius, take the average location, move it to the average location again, etc. And it ends up moving towards the center of a cluster. Any questions about that? No. Okay, great. So that's mean shift with just one cluster. How mean shift actually works is you take a bunch of centers and scatter them around the data, and they will all move to the center of clusters. And you don't need to know how many clusters you have, because some of the centroids will just move on top of each other, and you'll have a bunch of groups of centroids where that will define the cluster. Here, I'll just show you guys. You'll have all of these centroids that start moving towards the center of clusters, and there's a lot of overlap. And what you end up having is each cluster will have its own little group of centroids, and you'll turn each group of centroids into just its own center, and bada bing, bada bam, you have your clusters. Any questions about how the mean shift translates to multiple mean shift centroids moving? No, that makes sense to everyone? Okay, cool. So, this one is a little more complicated, but it's also very, very cool and very fun. So this one is called dbScan. DB stands for density-based spatial clustering of applications with noise. Wow, that's a lot of letters. What does it actually mean? So essentially what this is it is a clustering method that that functions kind of as a path. So what it's going to do is it's going to look at a data point and it's going to check the data points around it. And if there are enough of those data points around it, it is going to assign it to that cluster. And then it's going to take all of the data points that it found that aren't part of the cluster and look at those, check all of the points around it. And yeah, let me just take you to the steps. Yes. So we set the core, the centroid, to a unvisited point, or not the centroid, but the core. So we set it to an unvisited point. Okay, it's moving, but then we're going to take a look at all points within a radius of epsilon. Epsilon's just a number. You can think about it as n, you can think about it as however you want. Don't let the number scare you, but you look at all the points nearby. And if there are less than a certain number of points, you're going to set it as a noise point. This means there's no points, there's not many points around it. It's kind of on its own. You set it to noise. You say, hey, this isn't part of a group. It's just noise. And if you remember earlier when we talked about anomaly detection, this is kind of how that would work. Then you're going to take all of the border points. That's what happens if there aren't enough points around it. If there are enough points, we are then going to take all of those border points that are within it, and those are going to become the new core points that we're looking at, that we're checking adjacent points to. And if there are enough points that are within the cluster, it's going to set that as part of the cluster rather than a noise point. And it's going to do this until it doesn't find any more. So it's going to do this around. And then what it's going to do is it's going to pick a new random point and repeat the process starting with a different cluster. So you can kind of think of dbScan as a clustering method that follows a path until it can't find any more points. And then it chooses a new random point and follows a path. And it can get clusters that are a lot more complicated. So if you look at this shape, if you look at this shape, it would be very difficult to do this with a normal clustering algorithm because this cluster is circular around other clusters. If you think about how the others work, how they kind of take the means and shift them, or if they just take the nearest neighbor, these would have a really tough time actually finding the clusters in this because it's literally just looking at the distance to the nearest cluster. And with a circular thing, it just wouldn't work. So dbScan has a lot of applications for data that wouldn't work for other clustering algorithms. Any questions about dbScan? I know I kind of rushed over it. We're not that pressed for time, but I want to give us some time for the code as well. No questions about dbScan. Makes perfect sense to everybody. Okay, cool. So just a quick overview, clustering as a whole, it's a method of grouping data points based on similar properties. So just to kind of reiterate what I was talking about a little bit earlier, we showed a lot of these visually with data points where we were talking about the closest data point, and this was in like, X and Y coordinate system. Let's literally look at the physical closest data point. In reality, what's actually happening is it's looking at the properties. Each data point might have something, let's say, age and height or something like that. And those would be mapped onto X and Y, and it would be doing this with the actual properties of the data points rather than just the location, if that makes any sense. So again, that's how it ends up grouping the data based on similar properties, because things that are closer together or, their properties are more similar will be grouped together in clusters. The algorithms we went over were k-nearest neighbors, where you look at each data point, find the nearest neighbors and the most common cluster of them, and assign that data point to that cluster. and this one is supervised, requiring training data. We saw k-means clustering, where you take a certain number of centroids and shift them around until they end up lining up with the actual clusters based on where the average location of the data points that are within them are. We also took a look at mean shift clustering, which is very similar to k-means, except instead it takes a window around a centroid and moves the centroid to the average location of the points within it. And it does this with a bunch of means, and they'll end up kind of colliding and forming little groups of means that are then each assigned a cluster. DB-scan clustering we covered, and it's more of kind of a path-following clustering algorithm that creates clusters based on paths around, or yeah. Okay. Now that will essentially wrap up the instructional. We're gonna have some time to actually work on the code base in a little bit, but I just covered a lot of stuff and we've got a little bit of extra time. So if you have any confusion, are there any questions? Because I'm very happy to go back over things that were confusing. No. Okay. Fantastic. So moving on. Now it is your turn. Here is the bit.ly. Also, there's a QR code there if you'd rather get it like that, but to the actual coding portion of this meeting, where we will be implementing k-means clustering with a couple different groups of data, including Chipotle locations across the US. So we're going to be looking at those and clustering them into clusters and seeing how the algorithms do with that. Cool. And do you want me to do the next part first before?
All right. Before we get into that, quickly, for people on recording and people who are here. Hey guys, I know this was supposed to happen like 2 weeks ago at this point. We had some weird technical issues, including getting a room and some other fun stuff. So, Skyjam, as a quick reminder for what this is, we're doing like a mini kind of hackathon competition for the first time ever this coming Saturday. It should be a lot of fun. We're going to reveal the actual thing you guys are going to be doing on probably Friday. There will be food, there will be prizes. Scan this QR code if you want food and you're going to be there, because otherwise we might not have enough for everyone. Yeah. Wait, what? I don't know. I scanned it earlier today. Scan the QR code real quick. It might need to be public or something, which could be on me. UCSC email? Yes, use your UCSC email then, if you're having issues. Anyway, scan this if you want to come. It's going to be from like, I think 2 to 7 p.m. this Saturday. We'll be having pizza. There will be prizes to be won. It should be a lot of fun. So come along. It'll be great. If you don't have anything going on Saturday. Yeah. Yes, it is going to be an individual competition. Feel free to work with people, but like only one person's gonna win the prize. So I don't, yeah, one submission per person. No groups. Yeah. Yeah. Yeah, we'll also be posting this in the Discord. We want to get a decent head count for people who are interested in planning on coming, just so we know how much food to order. So fill this out if you're planning on it. I don't know, by like tomorrow, so we can get a nice little gauge for ourselves. This will also be used for like probably some fundraising stuff as well. So yeah, thanks guys. It'll be a lot of fun. I'm really excited to see how it goes. And if it goes pretty well, then we'll probably be doing this again in some sort of way. Anyway, with that, I think it's code time, so we should end the recording. Rest is you.